Building code requirements for electrical plans fluctuate significantly depending on the specific jurisdiction in which construction is taking place. In many instances, the requirement for electrical plans to accompany building permits is contingent upon the complexity of the electrical installation itself. If the proposed electrical work is relatively straightforward, local authorities may not mandate the submission of detailed plans. Conversely, for intricate or extensive electrical systems, the submission of electrical plans becomes a prerequisite for obtaining the necessary building permits. Furthermore, local building codes can explicitly stipulate the requirement for electrical plans, irrespective of the installation's complexity. Therefore, understanding the specific regulations governing the area is crucial. However, the involvement of a UL inspector, who is responsible for conducting electrical inspections, can influence the necessity of electrical plans. Should the UL inspector be satisfied that the electrical installation adheres rigorously to the applicable codes and standards, they may exercise their discretion to waive the requirement for electrical plans. This decision rests on their professional judgment and assessment of compliance. Regarding the payment of inspection fees to an electrician while a building inspector also conducts their own electrical inspection, this matter is typically governed by local policy and practice. Some jurisdictions operate under a framework where both the building inspector and a licensed electrician are mandated to inspect electrical installations. In such cases, the electrician's inspection provides an additional layer of scrutiny, ensuring adherence to safety standards and code compliance. The electrician's fee covers the professional services in inspecting the electrical rough-in, which occurs during the initial stages of installation, and the final electrical installation, which takes place upon completion. However, other jurisdictions may empower the building inspector to perform electrical inspections independently, without requiring a separate inspection by a licensed electrician. The legality of a building inspector conducting electrical inspections hinges on the laws and regulations specific to the jurisdiction in question. In certain areas, building inspectors may be authorized to perform electrical inspections contingent upon meeting specific criteria. These criteria often include possessing the appropriate credentials, such as certifications or licenses, and demonstrating relevant experience in electrical work. To ascertain whether a particular building inspector is qualified to conduct electrical inspections, it is advisable to consult with the local building department or licensing agency. These entities can provide definitive information on the inspector's qualifications and legal authority. It is essential to ensure that the electrical installation adheres to all applicable building codes and standards, irrespective of whether electrical plans are required. Compliance with these codes is paramount for ensuring safety and preventing potential hazards. The building inspector wields the authority to enforce the building code and, if necessary, issue stop work orders if the electrical installation fails to meet the stipulated requirements. These orders can halt construction until the identified deficiencies are rectified and compliance is achieved. To ensure a smooth and transparent inspection process, it is prudent to engage in open communication with the building inspector. Discuss the electrical inspection process in detail to gain clarity on the specific requirements and expectations. This dialogue can help prevent misunderstandings and ensure that the electrical installation meets all necessary criteria. When considering electrical installations, several key aspects must be carefully evaluated to ensure safety, compliance, and optimal performance. These aspects include conductor sizing, overcurrent protection, grounding, wiring methods, and specialized equipment. Conductor sizing is a crucial element in electrical installations, involving the selection of conductors with adequate ampacity to safely carry the intended load current. The National Electrical Code, or NEC, provides comprehensive guidelines for determining the appropriate conductor size based on factors such as ampacity, temperature rating, and application. Using undersized conductors can lead to overheating, insulation damage, and even fire hazards. Overcurrent protection is another fundamental aspect, aimed at safeguarding electrical circuits and equipment from excessive current flow caused by overloads or short circuits. Overcurrent protective devices, such as circuit breakers and fuses, are designed to automatically interrupt the circuit when the current exceeds a predetermined threshold. Proper selection and coordination of overcurrent devices are essential for ensuring reliable protection and minimizing the risk of damage. Grounding is a critical safety measure that establishes a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices and minimizing the risk of electric shock. Grounding systems typically involve grounding electrodes, grounding conductors, and equipment grounding conductors. Effective grounding ensures that metallic enclosures and equipment are maintained at a safe potential with respect to ground. Wiring methods encompass the techniques and materials used to install and support electrical conductors. Various wiring methods are available, each with its own advantages and limitations, including conduit, cable, and raceway systems. The choice of wiring method depends on factors such as the environment, voltage level, and mechanical protection requirements. Adhering to recognized wiring practices is essential for ensuring a safe and reliable electrical installation. Specialized equipment refers to electrical devices and systems that require specific installation and operation considerations. Examples of specialized equipment include transformers, generators, motors, and control panels. These devices often have unique requirements related to wiring, protection, and ventilation. Consulting manufacturers' instructions and adhering to relevant codes and standards are crucial for ensuring the safe and proper installation of specialized equipment. Regarding the National Electrical Code, or NEC, this is a comprehensive set of standards and guidelines for electrical installations in the United States. It is developed and updated by the National Fire Protection Association, or NFPA, and is widely adopted by state and local jurisdictions. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. Several key NEC articles and tables are particularly relevant to electrical installations. NEC Article 220 provides requirements for calculating branch circuit, feeder, and service loads. Accurate load calculations are essential for determining the appropriate size of conductors, overcurrent devices, and equipment. NEC Article 250 covers grounding and bonding requirements, including the selection and installation of grounding electrodes, grounding conductors, and equipment grounding conductors. Proper grounding is crucial for ensuring electrical safety and minimizing the risk of electric shock. NEC Article 300 provides general requirements for wiring methods and materials, including conduit, cable, and raceway systems. Adhering to these requirements ensures that electrical wiring is installed in a safe and reliable manner. NEC Article 310 covers conductor requirements, including ampacity, temperature rating, and installation requirements. Selecting the appropriate conductors for a given application is essential for preventing overheating and ensuring safe operation. NEC Table 310.16 provides ampacity ratings for insulated conductors rated up to 600 volts, based on temperature rating and installation conditions. This table is widely used for determining the appropriate conductor size for various applications. NEC Table 250.122 provides minimum equipment grounding conductor sizes for various overcurrent device ratings. Proper sizing of equipment grounding conductors is essential for ensuring effective grounding and minimizing the risk of electric shock. In addition to the NEC, other relevant codes and standards may apply to electrical installations depending on the location and type of installation. These may include local building codes, state electrical codes, and industry standards. Consulting with a qualified electrical engineer or contractor can help ensure that all applicable codes and standards are met. Understanding voltage drop is crucial for maintaining proper voltage levels at electrical equipment and ensuring optimal performance. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Several factors influence voltage drop, including conductor length, conductor size, load current, and power factor. Longer conductors, smaller conductors, and higher load currents all contribute to increased voltage drop. Power factor also plays a role, with lower power factors resulting in higher voltage drop. Various methods can be used to minimize voltage drop, including increasing conductor size, reducing conductor length, and improving power factor. Using larger conductors reduces the resistance of the circuit and lowers voltage drop. Shortening the conductor length also reduces resistance and voltage drop. Improving power factor can be achieved by using power factor correction capacitors, which reduce the reactive component of the current and lower voltage drop. Calculating voltage drop involves using Ohm's law and considering the impedance of the conductors. Ohm's law states that voltage drop is equal to the product of current and resistance or impedance. Voltage drop calculators and software tools are available to simplify the calculations. Understanding short-circuit current calculations is essential for selecting overcurrent protective devices with adequate interrupting ratings. Short-circuit current is the maximum current that can flow in a circuit during a short-circuit condition. If the interrupting rating of an overcurrent device is less than the available short-circuit current, the device may fail to interrupt the circuit safely, potentially leading to equipment damage or fire hazards. Short-circuit current calculations involve determining the impedance of the power source, conductors, and equipment in the circuit. The impedance of the power source is typically provided by the utility company. The impedance of conductors can be calculated based on their length, size, and material. The impedance of equipment can be obtained from manufacturer's data. Various methods can be used to reduce short-circuit current, including increasing the impedance of the circuit and using current-limiting devices. Increasing the impedance of the circuit can be achieved by using longer conductors or adding impedance in the circuit. Current-limiting devices, such as current-limiting fuses and reactors, are designed to reduce the magnitude of short-circuit current. Performing arc flash hazard analysis is crucial for identifying potential arc flash hazards and implementing appropriate safety measures. An arc flash is a dangerous electrical explosion that can occur during a short-circuit condition. Arc flashes can generate intense heat, pressure waves, and toxic gases, posing a significant risk to personnel. Arc flash hazard analysis involves determining the incident energy and arc flash boundary for various electrical equipment. Incident energy is the amount of energy that a person would be exposed to during an arc flash event. The arc flash boundary is the distance from the equipment at which the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for a second-degree burn. Arc flash hazard analysis is typically performed using specialized software tools that consider factors such as voltage, current, and equipment configuration. Based on the results of the arc flash hazard analysis, appropriate personal protective equipment, or PPE, can be selected to protect workers from arc flash hazard. PPE may include arc-rated clothing, face shields, and gloves. Implementing safe work practices, such as de-energizing equipment before working on it, is also essential for minimizing the risk of arc flash injuries. The most common voltages encountered in electrical systems are 120 volts, 208 volts, 240 volts, 277 volts, 480 volts, and 600 volts. 120 volts is commonly used for residential lighting and receptacle circuits. 208 volts is commonly used for three-phase power in commercial and industrial buildings. 240 volts is commonly used for residential appliances such as ranges and dryers. 277 volts is commonly used for commercial lighting. 480 volts is commonly used for industrial equipment and large motors. 600 volts is commonly used for high-power applications in industrial settings. Understanding the characteristics of different types of electrical equipment is essential for selecting the appropriate equipment for a given application. Transformers are used to step up or step down voltage levels. Generators are used to generate electricity. Motors are used to convert electrical energy into mechanical energy. Control panels are used to control and protect electrical equipment. Proper selection and application of electrical equipment are crucial for ensuring safe and reliable operation. Regarding the proper use of electrical test equipment is essential for troubleshooting and maintaining electrical systems safely and effectively. Multimeters are used to measure voltage, current, and resistance. Clamp-on ammeters are used to measure current without interrupting the circuit. Insulation resistance testers, also known as megometers, are used to measure the insulation resistance of conductors and equipment. Ground resistance testers are used to measure the resistance of grounding systems. Power quality analyzers are used to measure voltage, current, harmonics, and other power quality parameters. Using electrical test equipment safely involves following proper procedures and wearing appropriate personal protective equipment. Before using any test equipment, it is important to read and understand the manufacturer's instructions. Ensure that the test equipment is properly calibrated and in good working condition. Wear appropriate personal protective equipment, such as safety glasses and gloves. To energize the circuit before testing if possible. If it is not possible to de-energize a circuit, use extreme caution and follow safe work practices. Never work alone when testing electrical equipment. Electrical safety is of paramount importance, and it is crucial to follow safe work practices to prevent electrical accidents. Always de-energize equipment before working on it, if possible. Use lockout/tagout procedures to ensure that the equipment remains de-energized while you are working on it. Wear appropriate personal protective equipment, such as safety glasses, gloves, and arc-rated clothing. Maintain a safe working distance from energized equipment. Never work alone when working on electrical equipment. If you are not qualified to work on electrical equipment, do not attempt to do so. Hire a qualified electrician to perform the work. Understanding and applying electrical codes and standards is essential for ensuring the safety and reliability of electrical installations. The NEC provides comprehensive guidelines for electrical installations in the United States. Local building codes and state electrical codes may also apply. Industry standards, such as those developed by the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI, provide additional guidance. Consulting with a qualified electrical engineer or contractor can help ensure that all applicable codes and standards are met. Continuing education and professional development are essential for staying up to date on the latest electrical codes, standards, and technologies. The electrical industry is constantly evolving, and it is important to stay current on the latest developments. Continuing education courses, seminars, and conferences are available to help electricians and electrical engineers maintain their skills and knowledge. Professional certifications, such as those offered by the International Association of Electrical Inspectors, or IE, and the National Electrical Testing Association, or NETR, can demonstrate competence and expertise. The responsibilities and liabilities of electrical contractors and engineers are significant, and it is important to understand the legal and ethical obligations. Electrical contractors are responsible for ensuring that electrical installations are performed in accordance with applicable codes and standards. Electrical engineers are responsible for designing safe and reliable electrical systems. Both electrical contractors and engineers can be held liable for damages caused by negligence or improper workmanship. It is important to carry adequate insurance coverage to protect against potential liabilities. Maintaining accurate records of electrical work is essential for demonstrating compliance with codes and standards and for providing a history of the electrical system. Records should include electrical plans, specifications, permits, inspection reports, and test results. Records should be stored securely and be readily accessible. Effective communication with clients, colleagues, and inspectors is essential for ensuring a successful electrical project. Clear and concise communication can help prevent misunderstandings and ensure that all parties are on the same page. Active listening and asking clarifying questions are important for understanding the needs and concerns of others. Professionalism and respect are essential for building trust and maintaining positive relationships. Regarding sustainability and energy efficiency considerations are becoming increasingly important in electrical design and installation. Energy-efficient lighting, appliances, and equipment can significantly reduce energy consumption and lower utility bills. Renewable energy sources, such as solar and wind power, can provide clean and sustainable energy. Smart home technologies can automate energy management and optimize energy usage. Considering the environmental impact of electrical materials and practices is important for reducing the carbon footprint of electrical installations. The life cycle assessment of electrical materials can help identify opportunities for reducing environmental impact. Recycling and proper disposal of electrical waste can minimize pollution and conserve resources. Staying informed about emerging trends and technologies in the electrical industry is essential for staying competitive and providing innovative solutions. The electrical industry is constantly evolving, with new technologies and applications emerging all the time. Smart grids, electric vehicles, and energy storage systems are just a few examples of the exciting new developments in the electrical industry. Attending industry events, reading trade publications, and participating in online forums can help stay informed about these trends. Understanding the principles of electrical project management is essential for completing projects on time and within budget. Electrical project management involves planning, organizing, and controlling the resources needed to complete an electrical project successfully. Effective project management techniques, such as scheduling, budgeting, and risk management, can help ensure that projects are completed efficiently and effectively. Working effectively in a team environment is essential for success in the electrical industry. Electrical projects often involve a team of professionals, including electricians, engineers, architects, and contractors. Effective teamwork requires clear communication, collaboration, and mutual respect. Delegating tasks effectively, providing constructive feedback, and resolving conflicts constructively are all important skills for working in a team environment. Adhering to ethical principles and professional conduct is essential for maintaining the integrity of the electrical profession. Ethical principles such as honesty, integrity, and fairness guide the behavior of electrical professionals. Professional conduct standards, such as those established by professional organizations, provide specific guidelines for ethical behavior. Maintaining a commitment to lifelong learning and professional development is essential for staying at the forefront of the electrical industry. The electrical industry is constantly evolving, and it is important to stay current on the latest technologies, codes, and standards. Participating in continuing education courses, attending industry events, and pursuing professional certifications are all ways to enhance skills and knowledge. The ultimate goal of all electrical work is to provide safe, reliable, and efficient electrical systems that meet the needs of the community. By adhering to ethical principles, following codes and standards, and staying current on the latest technologies, electrical professionals can contribute to a safer, more sustainable, and more prosperous future.